All right, recording is rolling. Welcome to Friday, September 15th. A bunch of you guys just turned in your projectile quiz. Thank you for doing that. I'll get those graded over the weekend. At this point, I've handed back all linear motion quizzes. Those are back in your guys' folders. So remember, you guys can write out corrections. If you like for partial credit back, just give that to me next week. I'll put a partial credit back in for you, right? Right. We're going to revisit this mystery cup from yesterday, tell you guys a little bit about pressure. We're going to continue those free body diagrams from yesterday. Okay, you guys remember that PowerPoint? You guys got your notes out for that. And then, okay, this is for my AP students, so you guys don't worry about that. But those textbook puzzles that I gave you guys, I know I gave this page, I gave you guys some textbook puzzles a few days ago. Those aren't going to be due for a while. I want to go over as many as I can in class. I've also got some labs and whatnot lined up next week. Okay. But I like to get papers in your hands so you guys have plenty of time to look at those questions and think about them. So by the time we're solving them, right? So, all right. So this mystery cup. Yesterday I showed you guys this right here. Let's get another look at this. Ooh, I see like a straw hole in the bottom. Flip it over. Oh yeah, there's somebody with like a straw hole here. And see if I can find schematic from yesterday. And so the story went like this. I filled the cup up halfway with water, and the water stayed in the cup, like no problem, right? Then I filled it to the brim, and the water was draining out the bottom, but the water level didn't just stop where it used to be perfectly fine before. No, like the entire cup drained. And puzzle for you guys was, can you figure out what's going on inside that cup to make that work? Who's got this figured out? Who figured it out? What's going on inside that cup? How do you do that? Something to do with maybe how fluids work? Oh yeah, what do you think? All right. Yep, Maya got it. Yeah. Exactly. Yeah, she's saying, well, the straw goes up the side. Yeah, exactly. Just like that. You're gonna draw a slot here. It's gonna go like that. All right. Now, why would that make this work? Well, let's step through step by step. No. Okay. So when you originally fill it halfway with water, yeah, so some of the water goes into the straw, fills it up to about there, but then it'll just stop, right? When you fill it to the brim, well, now it's going to flood the whole straw. Oh, and you guys know how like the ball wants to roll downhill, your Hot Wheels cars want to roll downhill, water wants to flow downhill. Well, like the lowest point in the system is like down here. Yeah, so it'll start draining out the bottom, right? But when the water level returns to like the halfway point, where it used to be okay before, well, now there's a difference. There's been a state change because this whole straw is flooded. So it all gets siphoned out the bottom. Right? If you guys ever look under a kitchen sink or like the back of a toilet, you'll see a similar type design for the pipes, right? There's like this, that type shape, right? So it'll siphon out. Right. Now, this only works if, like part of what makes this work is the fact that this is all in a pressurized atmosphere. Like this wouldn't actually work in a vacuum. Right? Water actually does something weird in a vacuum at room temperature. Do you guys know if you put a cup of water at room temperature in a vacuum chamber or like in space, what does it do? Boils. It boils. It does boil, right? But it doesn't boil because it's hot. Like you could touch it, it wouldn't actually like scald you, right? It boils because of lack of pressure, right? Which is a weird way to think about boiling because we've always been like one pressure of atmosphere in our lives, right? Right. But it's part of what makes this work. Because if this were in a vacuum, what would happen is when the water level got back down to this halfway level and this whole straw is flooded, it would actually just break open here and part would fall left and part would fall right, and then the whole process would just stop, right? Right. But it can't do that if it's all pressurized because you can't just like open up a vacuum here. It's not what's going to happen, right? But maybe that gives you a hint as to the limitations of this because we do have like a finite amount of pressure that we're in. We're in 1 atmosphere pressure. I wonder what that means, like in a different context, right? And I wonder what that also means for like some kind of maximum height here. Like, suppose you're driving across the country, right? And you're seeing like these roadside attractions, like, oh, here's the world's like largest ball of yarn, right here by the interstate. Right? You keep driving, and oh, hey, here's Mr. Griffin built the world's largest Pythagoras cup right here on the interstate. Hey, how tall could this be, H, before it like maximizes out? And this wouldn't actually work anymore because there's not enough atmospheric pressure. Does anybody know like how tall I can make that Pythagoras cup before it actually doesn't work anymore? It has something to do with like the pressure on Earth, right? Maybe on different planets just work out different because of different atmospheres, right? Right. Well, hold on to the idea because I'll give you guys a so yes, some pointers about how pressure works. Okay, it's going to answer that question. Okay? So 1 atmosphere of pressure that we're in, 1 atmosphere of pressure. Okay. Now, guys, what is pressure? Pressure is a ratio of what to what? How about this? Let's do American units. You guys are pumping up your bike tires. What's the unit for pumping up your bike tires? PSI? PSI, right? And PSI, what does that stand for? Pounds per square inch. Pounds per square inch. Okay. Now, as units, American units could be pounds per square inch, right? Let's generalize it in terms of variables. Pounds measures a what? Force. Square inches is some kind of what? Area. Ooh, okay, so force per unit area. Ooh, okay. Now let's look at different units for pressure. Right. Well, PSI, you could say PSI is pounds per square inch. You could call that like an American units, right? That's pressure, right? But in this class, we almost exclusively use metric system. So in the metric system, what are we measuring force in? Newtons. And what are we measuring area in? Like square meters, right? Square meters. So there was a name for this unit. It has a special name in the metric system. Does anybody happen to know what it is? It's called a Pascal. So 1 Pascal, this stands for Pascal. How you write that, right? Is 1 Newton per square meter. Here's what that means. Right? You guys see this 100-gram lab mass right here? 100 grams? Oh, whoops, sorry, that's a 50 grams. Right, so next to it. 100 grams. Here we go. A bit bigger. Right. So this weighs 1 Newton. I feel 1 Newton of gravity force. It's like 0.98 newtons, but I'll call it 1 Newton. Okay? You guys see those floor tiles? Floor tiles? Can you guys count 3 by 3, like 9 floor tiles? That's pretty close to a square meter, right? Not exactly, but pretty close. What if you had a big old foam board that was 1 square meter, and you had one of these sitting on that foam board? That would be 1 Newton per 1 square meter. That would be 1 Pascal. Ooh, you guys see that? Okay. Now let's look at atmospheric pressure. 1 atmosphere of pressure. That's another way to quantify pressure. There's 3 ways to quantify pressure here. Pounds per square inch, pascals, atmospheres. There's another way called bars or millibars. Okay? There's also, sometimes you call it with millimeters of mercury you can do. Okay? Anyway, 1 atmosphere. Do you guys know how many either PSI or pascals that's also equivalent to? Does anybody know? Yeah, that's it. It's like 14.7 pounds per square inch. Right, maybe I should write it this way. Pounds per square inch. I like the fractions, right? So, right. Anyways, yeah, it's the same thing. Right. No, hold on. Pause right there. Pause right there. 14.7 pounds per square inch. Guys, how much does a bowling ball weigh? About 10 or 15 pounds, something like that. 10 or 15 pounds per square inch. Whoa! Is it like we have like a bowling ball on every square inch of our skin right now? That's what that means. Whoa, right? But you definitely notice the absence if you're like in a vacuum chamber. Like, I'm in a vacuum chamber. Your fluids will start to boil, probably die pretty fast. Right? So it's definitely not that. Oh, we're under a lot of pressure. Ooh, that's a lot of pressure, isn't it? Does anybody know in pascals how many pascals that is? It's like 101,000 pascals. Right? Also called 101 kilopascals. Ooh, you like that, right? Is that? Right. Sometimes like heights of fluids are used. I think it's like 76 centimeters or no, 76 centimeters of mercury. I think it is something like that, right? But let's use a pool example. Let's go to a big old pool of water, or maybe the ocean or something, right? So let's say you're standing on the ground, and oops, I guess the ground's like level, right? And then here's a pool of water, and this pool of water goes real deep. Right? You're standing on like the deep end of a very deep pool, okay? And you want to jump down, and you want to dive down, and as you go down deeper, 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 you can feel that pressure going up, 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 right? Now here at the surface, before you ever jump in the water, we're all experiencing 1 atmosphere of pressure. How deep do you have to dive to get another atmosphere of pressure from just the water? Does it say like you double to 2 atmospheres, right? How deep do you have to dive to add another atmosphere? Does anybody know? Right? It's about about 10.3 meters, about 10.3 meters, about 30 something feet. Ooh, that's pretty dang deep, isn't it? Right? Like 10 meters deep. Right? Now, people figured this out way back in the day. They used to like have, say, like town on top of a hill, and then there'd be like a lake down in the valley. Suppose this is a lake now, right? Down the valley. Say, hey, a few hundred years ago, there was, hey, we could just like pump water up, and then we don't have to like drag it up with the well. We could just like pump it up, like the early pumps and stuff, right? And then all over Europe, they started to do this, like pumping up water up hills from the lakes below. Except some towns were too high up for the water to pump up. It would only go so high, and then it would stop and say, "Oh, we're too far up." Guess how far too far up is? How high can you pump water before it runs out? H max is 10.3 meters, right? If your town is above about 10 meters, you might be able to do it in stages. You know, let's do 5 meters and dump it at 5 meters and dump it at 5 meters and dump it. But you can't do the full, like if it's 15 meters up, you can't do it all in one shot, right? Because there's not enough pressure to push it down. Kind of like the straw of how the principle of how a straw works. Suppose this guy's got a straw. It's like, ooh, I got a really long straw. I'm gonna drink this water. Oh yeah, right, it's got a straw, right? Right. The longest straw you could ever use would be like this, right? Before you run out. Okay, let's go back then to this right here. Now I've got my world's tallest Pythagoras cup. Guess how high I can make that cup where it's not going to work anymore? Like 10.3 meters, right? 10.3 meters. I actually guess it would like go down here. Like this height could be up to 10.3 meters. Right? At that point, it's got to open to a vacuum. It's just not going to work anymore. All right, so that was a fun adventure in pressure. There might be some pressure questions come up here and there. Right, so 1 Pascal is 1 Newton per square meter. All right, you guys ready to continue free body diagrams from yesterday? Free body diagrams. Let's flip my screen over. Ooh, guess we got the last. Let's undo all these. You guys are seeing all the ones we're going to do today. Okay, well, here, yesterday, this is about where the bell was ringing about-ish. Right? So we had this roller coaster on top of a hill. Now, if it's approximately at rest, and the weight and the normal force would be balanced out, right? What if it's going really fast over the top? Does the weight change? No, but it might feel like it if you're sitting in there, because what happens to the normal force if you're going really fast over the top? It would decrease a little bit, right? Be like like partial free fall. If it's like flying over the top, right? That might go to like 0, right? You like fly off the track. Right? Okay, so that aside, let's plummet this roller coaster down to the bottom. Right? Now at the bottom, what forces are acting on it? Is there still a weight? Yeah, there's still a weight. M times G, right? Mass times gravity field. Still got a weight, right? All right, now here's where I'm going to introduce an idea that's going to come back a few weeks from now, right? Something to do with the fact that it's on a curved path and it's moving forward. Right? As it's moving forward, it can't continue to move straight forward. You guys see it's going to be forced to move like up into this loop. So it's going to have to like change direction. So the fact that it's on a curved path, right? And if you were sitting inside that roller coaster, you would feel really what? Really light or really heavy at that moment. Really heavy. Especially like the tighter this curve and the faster you're going, you would feel heavier and heavier, wouldn't you? Somebody being on a curved path. What do you think the normal force looks like at that point? Really big, really big. So that there is a net force on that car, right? And that net force is causing it to something to do with like changing direction. The net force is called the centripetal force. Like if you subtract this two, it's something called centripetal force. There's an equation attached to that, something to do with how fast it's going, something to do with the radius of curvature. I just want to plant that idea today, and then in the future, that's going to come back. Okay. Right, one more deal with this roller coaster. What if it's at the top of the loop and it's going around? Right. Now, I gave you guys a velocity vector. Remember, the velocity vector is not actually part of the free body diagram, but it does provide important context. Because if that car was not moving, then what would it be doing? Falling right off the track, right? So it better be in motion, otherwise it's not going to make it around. Right? Or if you don't like the roller coaster, maybe if there's a marble that goes around, it's a similar idea, right? So what's one force on that coaster? Its own weight, its own weight. Okay, I mean, that one just keeps being the same over and over, right? Earth's gravity pull doesn't change, right? The weight, right? Right. What other forces also acting on that coaster? Is the track pushing on it? What's the name of that force? The normal force, right? Which direction does that normal force point? Down, right? Are there any other forces on that coaster? No, that's it. That's the whole story. In terms of free body diagram, we're still ignoring air drag a little bit. It's probably negligible anyway. Right? That's it. Now, those two forces are conspiring to act as what's called the centripetal force. And something you do with like the radius of curvature there, something you do with how fast it's going. Okay, just plant that idea now. Right, that's the free body diagram at that point. Right. Do you guys see any upward forces? No. Although if you're along for the ride and you have your eyes closed, you might think you're being thrown upward, but there actually is no upward force there. Interesting, right? There might be an upward force on the track from the car. That'd be Newton's third law force, but on the cart itself, there's only downward forces. Right, car brakes to a stop. This is one of my new posters. See, while you guys are getting that one in your notes, I'm gonna on the camera, just on the thumbnail. So if you're watching this, oh wait, did Zoom do away with that? Yeah, I think they did. Here, let me switch my screen real fast. Right. Last year, I think there used to be like a little thumbnail when I switched screens, but that's since changed. So there we go. Flip over, flip back. All right. So this is one of my new posters. If you're in class, you guys see the poster over there on that wall. Car brakes to a stop. Right. So what's one force acting on that car? I mean, its weight is the first one I'm going to because if there's no weight, if it's just flying through space, there's probably nothing else going on. Right. But it's not in a free fall because there's a what acting on it also? A normal force, right, from the road. Now, as long as the road's flat, those two are going to be the same magnitude, right? And if I stopped right there, that car would either be at rest or it'd be constant velocity, right? From the free body diagram, it could be either one of those cases. Right? If it's braking to a stop, which direction does the friction force point? To the, well, opposite of the direction of motion, right? Car's moving to the right, there's got to be a net force to the left, so it can accelerate to the left, hence braking. Okay, right, is that? Right. Maybe that's the friction between the tires and the road, but I'll just say it's acting on the car like center mass, right? Okay, right. I said. Car drives around a curve, as seen from behind. You know, I have a poster for this one too. Imagine a couple of taillights. Can you guys imagine? You guys see a license plate right here? You guys are imaginative, right? Okay. We're following this car from behind. Let's say it's making a left-hand turn. Okay. So this car has a weight. This car has a normal force holding it up. Right? Now, if it's making a left-hand turn, it's on a flat road. Suppose it's on a flat road. I should have specified that too. Flat road, right? What force is allowing the car to make a turn? What kind of force is that? Think about this. I know we're in Florida, so we don't get icy roads very often. But suppose you're driving on an icy road, right? And it's a flat road, and you have to make a turn. Do you have to be really, really careful about making that turn? Maybe you want to slow down and make sure you don't like break. You need friction, right? Friction's going to allow the turn, right? That's what I'm looking for, friction, right? If you had a dry road, probably be a lot easier to make that turn. You could probably make it a little bit faster, right? So friction is allowing the turn to be made. So that car is turning to the left, turning to the left. Oh, okay. Okay. You guys get that? Here, good here. Right. Now, if the road was banked, would it be easier to make the turn? Definitely. In fact, you might not even need any friction at all if you know the radius of curvature of the turn and you know the speed limit. You might be able to, as an engineer, calculate what the ideal bank angle would be. But on a flat road, you need that friction right there. Okay. Block hanging at rest from a spring attached to a ceiling. Ooh, is that block being pulled down with a certain weight? Yep, there's the weight on that block, right? But it's not a free fall. What's holding it in place? The force from the spring, right? And if it's at rest, that's a type of equilibrium. So those two forces would be the same magnitude. They would be zeroing each other out. Right? Oh, and you guys know something about spring force. You guys remember Hooke's law, F equals kx? Right? So something to do with like how stiff the spring is and how much the block stretches it. That would be F times x, right? F equals kx. Right? In fact, if you knew enough things, like if you knew, say what planet you're on and the mass of the block, so you got the weight of the block, and you know how stiff the spring is. I bet you could calculate how much it's going to pull the spring down. Right? You can do that, right? And then in the future, if you want to add a layer of complexity to this, you could pull the block down further and let it go, and you're be oscillating. In that case, I bet the spring force would be changing. A bottle rocket, we're going to blast it upward through the air. Let's throw an air drag. Why not? Okay. Bottle rocket being blasted. Let's say it's accelerating even. It's accelerating, so there's a net force. Right? I think this rocket's going to have a weight. Okay, right. I bet there's going to be some kind of thrust force. And if we're also considering air drag, then the air drag would oppose that, right? It would oppose the direction of motion. So probably also that way too, right? They said, do you guys see how the thrust force is beating both the weight and the drag? Therefore, there's a net force. Therefore, that rocket at that moment is still accelerating, right? The net force is the difference in all those, right? Divided by its mass. We give you the acceleration. Right? Oh, where does that thrust force actually come from? It's from the exhaust gases being pushed out the back of the rocket. Right? So the rocket's pushing the exhaust gases out the back. And the Newton's third law force to that, the equal and opposite force, is what pushes the rocket forward or up. Baseball flying through the air at 45 degrees to the horizontal. Right. So maybe somebody hit this baseball or we threw the baseball and it's going on like a projectile path, like a parabola path. Right. And at this particular moment, it's going like 45 degrees up and to the right. Right. Does this baseball have a weight? Yep. Right. Now, if you said there's no air drag, then would that be the whole story right there? If there was no air drag? That would be the whole story. Right? In fact, if you just had the free body diagram, would you even know the direction of the baseball? You wouldn't. It would be ambiguous. If all I gave you is the free body diagram, if I didn't give you that green velocity vector and you just had the free body diagram, you wouldn't know if that baseball was going straight down or straight up or straight to the side or off on some angle, because that free body diagram applies to all those cases. That baseball going through the air in that parabola path, every single point on that parabola path would have the exact same free body diagram, which is that right there. Right? That's as long as you ignore air drag. Are you guys ready to add air drag to the mix? Add air drag? You guys tell me, if I add air drag, which direction is the air drag going to point on that baseball for that situation? Which way? Would air drag oppose the motion of the baseball? Right? Right. And since the baseball is going up to the right, that means air drag points down to the left, right? I guess that. Right. Now, think about this. As you guys are finishing those notes, the fact that the baseball is always changing its direction, it's on this parabola path, it's always changing direction, it's always changing speed. I remember from yesterday, air drag is proportional to the square of the speed. Ooh, that's a lot of things changing all at once. The speed's changing, the direction's changing. Air drag is proportional to the square. Right. You guys see how if you consider air drag, this could be a much more complicated problem really fast. Maybe you need some kind of computer model to solve it, right? It would probably be the best way, right? Where does the baseball actually land with air drag? Ooh, probably a little bit short of where it would land if it was a perfect parabola. Right? Okay, guess that. Do people pull a stubborn donkey? Ooh, aerial view. So we're up in a helicopter, looking straight down on this donkey being pulled. Do you guys think there's a tension in this rope and a tension in this rope? You guys think tension is a type of force? Yep. So there's like the leftish tension and the rightish tension. I guess it's like forward to the left and forward to the right. You guys see that? Right. Now, if the donkey is not moving, hey, not moving is a type of equilibrium. Do you think the donkey has his hooves dug into the ground and there's some kind of friction force going on too? Right. That might be like that right there. Right. So the donkey's like dug in and not moving. Right? Now, what I tried to do, I may have misdrawn this a little bit, but what I was trying to get at was, do you guys see how the two tension forces are canceling out left and right? Right. Like forward to the left, forward to the right. That leftward component and that rightward component are canceling out. Right. But they're both pulling forward. And those two forward components adding up are supposed to cancel out with the friction going back. And I know they cancel out because not moving is an example of equilibrium. Right, you guys remember about that? Let's flip my screen back over here. Right, because one of the recent labs, guys. There we go. Right, you guys remember this right here? Right, that is the donkey problem, isn't it? Right. Except this is vertical and this is a weight. But if you just turn it horizontal and make it aerial view, it's the same concept. Right. You guys see that? Forces in 2 dimensions, right? Equilibrium. Donkey. Block at rest on a ramp or an incline. Right? So there's a whole class of classic physics problems that involve this block on this incline. In fact, your guys' Hot Wheels cars were sort of a version of this too, in a way, right? They weren't at rest, but they were in motion, but similar idea. So what are we going to do with this? Now, this is going to be a process question. You guys remember how projectiles were processes? It's like, okay, well, first figure out the vertical and horizontal components, and then figure out the time it's going to be in the air, and then figure out what's going on vertically, what's going on horizontally, where's it going to land, where's it going to land. Okay, so there's like a whole process that you had to follow. Similar type idea here. Whenever you see a block on an incline, okay, so this thing has a weight that's pulling it down. I mean, if that wasn't there, If it's just floating around in space, probably nothing else exciting is going on. Okay, so you got to have a weight to make anything else happen. Okay. Then what you want to do, you always want to, bam, bam. Do you guys see a couple of axes? And the axes are parallel and perpendicular to the surface. You guys see that? Right. So it's like a rotated Cartesian system. It's not parallel and perpendicular to gravity. No. It's parallel and perpendicular to that surface. And everything else in this problem, we're going to think in terms of that rotated Cartesian system. Right? You guys got that? Right? You guys got rulers on your desk and you're like dash, 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 dash. Right? Dash off some coordinates like that, some axes. Right. Well, right away, I see that that weight is not aligned with that rotated Cartesian system. So I'm going to have to break it into components that are aligned with that system. That weight is partially pushing the block into the incline, but partially trying to make it like drag along the incline, like down the incline too, right? Okay. So here's what that looks like. Bam. Hey, do you guys see a nice right triangle right there? You guys see a nice right triangle? I see a right triangle. You guys see that right triangle? Guys, where is the right angle in that right triangle? Is the right angle down here? It is not. Is that right angle right here? Bam, there's the right angle, right? So it's where the two components turn right there, right? So that sine component, you guys see mg times sine theta? Is that parallel to the floor, like this way? No. Is this parallel to this surface? Ah, it is, or this axis, if you like. This axis, this surface, mg sine theta. You guys see how those are all parallel? All parallel? Here, let me flip my screen over and show you guys the poster version of this. Okay, because I got posters on the real important ones, right? This is a real important one here. Okay, so here's the weight, right? Here's the Cartesian system, the axes, right? The x-axis, y-axis, right? And then I'm going to break this weight into components, bam, bam, so that this mg sine theta right here, you guys see if I hold my ruler up to that and go, it's parallel to that surface, parallel to that axis, bam, bam, bam. You guys see that? Notice this is not drawn like this. No, that's a really common mistake I see. Students want to go like, no. So, bam, just like that. So this is parallel to this. You guys can do parallel lines, right? Right? You guys can do parallel lines in your notes. You guys are drawing parallel lines, right? Students always struggle with this, even if I make a big deal about it. Right? So I'm taking some time to really emphasize this point. Okay? These are parallel. You guys see parallel? You guys draw parallel lines, right? Parallel, right? Is good. Okay. Okay. Well, since I got the poster here, let's look at the other forces. Do you guys remember normal force? Guys, what does normal mean mathematically? If two lines are normal, that means they're what? Perpendicular. Okay. Ah, so is this normal force perpendicular to the surface? Yeah, like by definition, it's going to be, right? The normal force always points normal to that surface. Ah, you see that one? Is that one? Right. Just eyeball it. Do you guys think this normal force might be a little bit less in magnitude than the weight? Right. It is for this incline situation. In fact, it's the cosine component. This normal force is actually balancing out how much the block is trying to push into the incline, right? So mg cosine theta, where I'm playing off this angle here. Oh, I meant to point that out too. Guys, is this angle theta always equal to this angle theta? Yeah, like if this is 29.7 degrees, then is this also 29.7 degrees? It is. It's always a match. This angle is always this angle. Okay, I'm not going to prove that in class, but if you're really curious, you can go on Google search or try it yourselves, but it's some fun geometry. But that's always that angle. Okay. So here's mg cosine theta, here's mg sine theta, right? Cosine and sine components. Guys, sine and cosine are never going to go away in this class. Okay. You guys saw it with projectiles, you guys saw it with the donkey problem, you guys see it here on the incline. Right. Right. So here's also mg cosine theta. Right. You guys that. Right. And if that's all you had, like your Hot Wheels cars, it was just those two. The weight down and the normal force like that, and the Hot Wheels cars would accelerate down. Something to do with the net force like mg sine theta. Okay? But if the block's in equilibrium, which might be at rest or it might be sliding at constant velocity, would be also equilibrium, then this friction force is balancing out the sine component of the weight. So this is equivalent to mg sine theta. Do you guys see that right there? It's a match. You see that? Just like this. There's a match like that. Is that? Right. Is that? So that would be equilibrium. Okay. Yeah. While I got my screen switched over, let's look at another poster. I just made this poster a few days ago. It's a new one. Oh yeah, new posters. So what if you change the angle of incline. Ooh, let's play around with that as a variable. Ooh, I see 5 different angles going on. So I only labeled one of them, like theta. Right? I see theta right here. Okay. But ooh, I see 0 degrees here. I see, maybe that's about 30 degrees-ish. That's about 45 degrees. That's about 60 degrees. That's about 90 degrees right there. Right, so what's happening to the free body diagrams for each of these, right? Well, the weight's always the same. The weight doesn't change, right? mg, but whatever. Right? But look what's happening to the normal force. Because what's happening to the normal force? It's getting what? Bigger or smaller? Smaller and smaller. With an increased angle, it's getting smaller and smaller. In fact, if the angle is 90 degrees, the normal force goes to 0. If you put a block up against the wall and then let it go, the wall and the block aren't pushing on each other anymore. It just goes to 0. There's no normal force here. Okay? So here's the rule: mg cosine theta. Just like we saw back here. mg cosine theta. Hey, it's the same thing. mg cosine theta. Hey, hey, hey. There it is, over and over. Guess that. Guys get that? All right. You guys ready for PowerPoint? All right, switch over back to the PowerPoint. Back to the PowerPoint. Ooh. All right, so let's finish this off. So we got normal force there. Notice the normal force matches the mg cosine theta. Right? And if the block is at rest, then I definitely also need a what kind of force? Friction force to lock it in place. And that one's going to match the mg sine theta. So you guys see the relationships going on? Right. One more detail. This friction force is related to this normal force by the coefficient of friction. So there's a relationship between these two also. Hold on to that idea. I'll probably come back to it in the future. Right? What if the block is sliding at constant speed down the ramp? Ooh, constant speed down the ramp. Hey, is that a constant velocity? Constant velocity, what's the acceleration? 0. So what's the net force? 0. Is this going to be identical free body diagram to the block at rest? It is. It's an identical free body diagram. Right? Technically, the one difference is that this is now kinetic friction instead of static friction. That's it. Right? But if you didn't know, if it was static or kinetic friction, if you just saw friction, just ambiguous, and you just had the free body diagram, you wouldn't actually know if the block was at rest or sliding down at constant velocity, because those would be equivalent free body diagrams. They'd both be equilibrium. Okay. Well, here, of course, I'm telling you the velocity just for context. Right. Okay. Okay. Guys good? All right. All right. One more of these inclines. The block is sliding up the ramp and slowing down. Ooh, due to, well, I said due to friction, but that wouldn't be the only reason it would slow down, right? Like, I bet if there was no friction, it would still slow down anyway. Right? What if you take a Hot Wheels car, and you give it a push, and it starts moving up the incline? It's still gonna eventually turn around and come back down, right? Right. So let's look at this free body diagram. Right. So the weight's the same. Here's Cartesian system. That's the same. Bam, bam. Components of the weight. That's the same. The normal force. Bam. That's the same. So far, it's been identical to the last couple of slides. There's been nothing different, right? But here's where things are gonna be different, right? Oh, guys, the friction force now points which way? Opposite of the motion. Look at that. Look at that friction force. See how it's opposite of the motion, right? As a rule, friction always does that. It's opposite of the motion, right? I bet that block's slowing down in a hurry, especially because of that friction force, right? Okay, so, well, could elaborate on that, but let me fit in the last couple slides before bell rings here. Right. Atwoods, really classic physics question. You guys gonna have whole labs involving these Atwoods. Guys, do each of those blocks have a weight? Right? You guys see the weights? Right. Now, if they're the same weight, is that just probably gonna hang at rest, or definitely be in equilibrium, right? What if M2 is like a kilogram and M1 is like just an empty string, like nothing? Would that M2 accelerate down at the full rate of gravity? It would, right? So there's your two boundary conditions. If they're the same mass, the same weight, it's in equilibrium. If all the weight's on one side, it accelerates down at the rate of gravity. But what if it's like 7 kilograms versus 3 kilograms? Do you think it's going to accelerate somewhere between 0 and g? Right? How would you make sense of that? There's some internal forces going on right there. There's different ways you can solve that. I'll have you guys solve it empirically first with the lab, and then we'll go through a process. Right? Here's a little extra stuff. Right, and here's the last slide in this PowerPoint. So you can also modify a Atwood, have like a horizontal type motion. So let's look at the forces here. So there's the weights. There's a normal force to balance out that weight to like effectively neutralize it. Right. There's also some internal forces, like this tension could be an internal force. Right. But there's only one external force driving the system, and that's the weight of M1. Right. Right. So you guys get there? All right, well, there's the bell. There's the bell. So you guys have a great weekend, and I will see you guys next week.
X-ray